So during the break, I was just showing people some of the resources available on the web to help you find thermochemistry. So this is the NIST webbook. And I'd say this would be is the most popular one in the world for looking up thermochemistry quickly. A disadvantage of this is no way, as far as I know, to get it to just download a lot of molecules for you. So you have to like read it. It's made to be a human interface. So it's displaying the NIST database in a nice human form very beautifully with a little story. But it's not dumping it to your program if you're trying to get 1,000 molecules for your mechanism. It's not the way to do it. And you can see they'll have a little story. They have references. You can click the reference. It'll show you what it was. You can see the error bars. It writes it down carefully what the equations are. I think this is a nicely done website. A not so good website is one from my group, but it has some nice things about it. So you can type in like some rates. You can type in some molecules. So here, if I type in like so say this is just propane. So I draw propane. There it is. And then it'll tell you some different representations of propane. These are like the CAS numbers, all this library stuff. If I click search thermochemistry, it'll tell me what it knows about propane. It knows propane from a DFT calculation. It knows what GRI mech, which is a famous mechanism, what it said propane was, using a different representation. There's a group additivity, and then it plots the different methods, things against each other. So you can see, for example, that the DFT QCI thermochemistry and the GRI thermochemistry seem to disagree at really high temperatures for the heat of formation of propane, or the heat capacity of propane.
Any estimation as to when your group will have published RMG that is capable of handling nitrogen?
We submitted it to the Combustion Symposium. It got rejected. We're rewriting the paper right now, soon. And I was hoping to show you that version now, but apparently didn't get done. My student was supposed to send it to me. So maybe later in the week. But we have a version that does nitrogen as well, but it doesn't have the thermochemistry for nitrogen compounds is much sparser than it is for the hydrocarbons. Here's the CCCBDB database. This is the computational chemistry database. And this is nice too. It has little tutorials about how you do calculations, what the units are, everything. It has a little story about the vibrational frequencies. It has a lot of stuff in here. And so it has, here we go, bad calculations. These are different calculations that fail dramatically in different ways, and they'll have a little story about that. So if people who are interested in how they use the quantum chemistry methods to calculate thermochemistry are really interested in this website, and they are trying to compare all the different methods and trying to figure out why some methods work better than others for certain kinds of molecules and stuff like that. So that's a very thing here, and this has a it tells you all about how to type in. So you can type in some molecule you want. Say I want C4H6. It could be any of these molecules. Let's do cyclobutene. And I'll look and see if they have any information on cyclobutene. Sorry, no experimental data available. Too bad. If I look up one in butine, let's see if anybody's done that one. Sorry, no experimental data. Let's try 1,3-butadiene. I bet you somebody's done that. So then if I went back to NIST and I type in, so actually this is something, maybe a good thing to keep in mind, is that each of these databases, there's no coherent national program or international program to try to make nice databases for people to use. Call your congressman and tell them that's what you want. But right now, no one's paying for it. And so people, when they have funds and they have energy, they make some database and then it kind of gets out of date because nobody takes care of it for a while, and then they get some more money and they fix it up a little bit. And then somebody else thinks their database stinks and they make their own. And then some other countries decide that they're not going to use some stinking American database. They're going to have their own database. And so they'll start a different one. And they care about different molecules, so have different molecules than this one and that one. And anyway, so that's just like all human endeavors, it's not really that coordinated. On the plus side, these days you can actually do automatic web searches and find all the numbers in all the databases. And then you can compare them to each other. And that's a good way to identify where there's potential problems if you see numbers that disagree. If you see the same number over and over again exactly, that usually means they're all coming from the same source, and they might actually all be wrong in the same way. So it actually gives the best confidence if you get several numbers that all differ a little bit, but they're pretty close. Then you feel like, oh, there's like a convergence in the community that we all agree on this number. But if you really care about it, you've got to look up the background, because all these things come from journal papers that somebody wrote based on some experiment or some calculations they did. And you can see some of these calculations are done a long time ago. So this is enthalpy measurements back in 1945 and 51 are apparently the best available ones for butadiene. Then there's a story about how people looked at this again in 62 and 76 and decided everything is okay. And anyway, see, this is the current state. It looks like there's no entropy value. Is that right? How interesting. So there's no entropy value for 1,3-butadiene, so that would be a good one to search and see if anyone actually has an entropy for it. That'd be a pretty important number. I'm sure that my students are using a number, so if you look in my database, you'll get some number. I have no idea how good our entropy number is for 1,3-butadiene. Anyway, so that's the kind of status of the world. There's a woman named Elke Goes in this lady here, Elke Goes, in Germany, who's trying to maintain a database that was originally started in Israel by a guy named Alexander Bearcat, and that one has a lot of really good numbers in it. Also some not so good numbers, but it's a pretty big database. So a lot of people use that one as well. It's called the Extended Third Millennium Ideal Gas Thermochemical Database or something like that. And then there's another effort in this by an organization called primekinetics.org. It's led by Michael Franklock at Berkeley. And that one also has a set of data, I say not as big as some of these other ones, but in some cases better. And it has a lot of tools to help to handle uncertainties and error bars and do different kinds of things with kinetics. So this is another good website to browse around on. And this is mine, the RMG. All right, back to the talk. All right, so the best numbers that are available now are, oh, come on. Yes, good. The active thermochemical database. And this was developed by Branko Rušik, who's at Argonne National Lab near Chicago. And there's a European kind of version of this too. So the way this works is when you're trying to compute enthalpies, the entropies and heat capacities are properties of a single molecule. But enthalpies are always referenced to, say, the elements in their standard states. So they necessarily require a network of reactions. You need some reactions to connect them to some other molecules. Now, the general problem is that, except for the elements in their standard state, so if you can do, for example, let's try to do one. So suppose I'm trying to compute the thermochemical properties of C6H7. This is one of my favorite molecules. Okay, so this is a benzene ring with one extra hydrogen stuck on it. Okay, so this is not stable. You can't buy it in a bottle. It's a little bit hard to make, a little tricky. So you want to, but this turns out to be pretty important because a lot of times you have benzene, like a flame, and you have a lot of H atoms. So you should make this stuff at least in equilibrium with it. So if it's in equilibrium, it should be, it depends on the thermochemical properties of this, of how much you're going to make. Okay, and then if you make this leads a way that you can start to open up benzene rings. which could be pretty important. Or vice versa, if you started with a cyclohexane, this might be an intermediate towards getting into benzene. Okay, so we care about this number. So I want to know thermochemistry of this. Well, the problem is I don't know how to do this. I guess I could say, well, maybe I could react an H atom plus a C6H6 to make that. That might be one way to do it. So the question is, can I figure out experiments where I would do this and measure something? So I can measure, maybe I measure the forward rate. Maybe I could also measure the reverse rate. And then I could, from that, infer an equilibrium constant. But that's only related to the free energy. It doesn't tell me the enthalpy separately. Right? It just tells me the delta G. So the entropy and the enthalpy are mixed up together, but I don't know either one. Now, somebody before figured out the enthalpy of hydrogen. So suppose I have H2 to 2 H's. Well, this is actually really, this reaction doesn't really work that way very well. So instead, somebody probably did this. They did OH plus H2 to make water plus H. And they knew the thermochemistry of water and hydrogen. And then they did something else to figure out the thermochemistry of OH. And then from that, then they can infer the thermochemistry of H atoms. And I need this number from this experiment in order to plug in here in order to infer the thermochemistry of this guy. Does that make sense? So my number I infer, if I could do this experiment, I rely on knowing the number for this guy in order to get the absolute value of the number of this guy. Okay, and this one is coming from some other experiment. And then maybe there's some photoionization experiment and some other experiments that also are relevant to the H atom and maybe also relevant to this. Maybe there's some other way to do it. Like, maybe I could come to this from C6H8 plus OH to C6H7 plus water. That might be another reaction I can measure. Maybe I could somehow do this. Okay, so Rushik and von Lazewski, this guy, they figured out an automatic program that keeps track of all the different linkages between different molecules and trying to make the linkages all the way back to the elements in their standard states in order to infer the enthalpies of formation of all the different molecules. And so here's a couple of them, but there's lots. There's lots and lots of different things. There's a big giant network of hundreds of different data on different reactions that are all relevant to the enthalpies. So here's a part of it. So this was all about hydrogen oxygen. So H atom is a very important one. OH radical, very important because we make a lot of this guys. And a lot of reactions for making other radicals involve these guys. And so water, they evaporated water. That's how they relate to the standard state. Here they did some bomb calorimetry. They figured out the heat formation of water. They ionized it. Then they did the dissociative ionization of water, using photoionization stuff to figure out something about it there, and so on and so on. So the current network at the time when this slide was made had 600 molecules and 3,200 secondary vertices of these things, I think. So 3,200 different data that affect this calculation of the enthalpies of formation of the 600 molecules. So you can imagine this gets to be kind of complicated. So they wrote a computer program to keep track of it all, keep track of all the error bars and all the measurements, and to calculate everything for you. And this is just the hydrogen oxygen part. They actually have nitrogen and carbon and lots of stuff in there. Now, when they did this, a really big news item, anyway, this is part of the math, how they keep track of all this, guys. This is a really big news. So in 2001, they used this, and they figured out that OH, the heat of formation of OH was wrong. So the heat of formation that everybody used, the NIST web book had, and everything for OH was incorrect. And so that was like a shock. The poor thermochemical community almost collapsed of heart attack. Because OH is the easiest radical to use to abstract an H from anything. So it had been used to attack everything in order to make the radicals. But so all the enthalpies of all the radicals in the world were basically based on assuming the value of enthalpy of OH was correct. But now it was incorrect. So all of the previous data had to be go back and reanalyzed to compensate for the fact that the OH was wrong. But then when you do it, so here was the JANF value of OH, was the error bar that big? And then somebody gave a number over here. And then when they did the Rusick wrote a paper here. Eventually, after they consider everything, they get this little tiny error bar. And they're really sure that is really the enthalpy of formation of OH. But this number over here is a lot different than the GenF number over there. Okay, so at like 2 kilojoules difference. Now, 2 kilojoules is not that big, but it's a lot, actually, when you try to figure out like equilibrium and stuff like that. So it really affects a lot of rate coefficients. You mess up all the forward, reverse rate coefficients. You know, one of them is wrong because of anyway. And so anyway, so here's the whole story of this. And actually, shortly after this, they discovered that the heat of formation of carbon atoms was wrong too. So then we were in really trouble. OH was wrong and carbon atoms were wrong. And then they also did HO2, which is extremely important for ignition. And again, the GenF number was way down here. And after they did a lot of work, they got the error bar down to this little semicircle there, which is, again, quite different. So it's 10 kilojoules off. So that's actually quite a huge difference. And so that completely changed all the predictions of the ignition models for everybody because of the HO2 thermo. And this shows you different methods of extrapolation, give you like different results. And you're happy when you actually get all the error bars overlap and you feel like you actually understand what's going on. And this was like a sequence of when they did different work. Things were they could see there was something was wrong because the error bars are not overlapping over a lot of the temperatures. And so after they went back and tracked down what the problem was, then now everything agrees. And so there was this story about a lot of people tried to measure this over the years, and they're all over the place, right? The numbers you can see. And so finally they decided it's this 2.94 plus or minus 0.006. And then they can. There's an experiment with OH plus NO2 making. This is in equilibrium with HO2 plus NO. And there's experimental data on this for a while. And there were a bunch of different papers about it with different models. And everything was problematic. And then finally, they got it straightened out here. Here's another example from the active thermochemical tables. This is very recent, 2012. Is that they wanted to know when methylene reacts with the H atom, it makes a CH plus an H2. Or in reverse, you get CH reacting with hydrogen, you get methylene plus H atoms. And this is a pretty important reaction in fuel-rich flames. And so here they used appearance energies from the photoionization experiments primarily, and then carefully propagated the whole network through and figured out the equilibrium constant for this reaction, the error bar and the equilibrium constant. And they needed to know this number both at 1,000 Kelvin and also at 10 Kelvin. So you had to be really careful. If you want to try to get something good at 10 Kelvin, it's actually pretty tricky. If you're off by any energy at all, you'll be completely wrong for the equilibrium constant. And then recently, 2010, these guys figured a way to do this all with just quantum chemistry. So if you have quantum chemical calculations, lots and lots of them, how to combine them and actually infer what the best estimate, theoretical estimate is of the thermochemistry. That's what this is about. I think I'll just go through this pretty fast. This is, if you look in the Bearcat Table, this is what it looks like to you. So there's methyl and the whole story about it. And these are some of the key species. If you really get into this, it's good to memorize actually some of these numbers for the species that matter the most to you, because they'll keep coming up over and over. And you'll be able to see, is this exothermic, is this endothermic, what's going to happen? Yeah, and also the typical bond energies. If you're doing a reaction, I'm always doing oxidation reactions, and so I have different fuels. I need to know which CH bond is going to be attacked by the different radicals. And so you can figure out which of those are exothermic and by how much, to get an idea of which are likely to be attacked. Now, there's a lot of molecules in the world, and each of those projects, I mean, you can see that it was only in the last 15 years that we even figured out the heat of formation of OH and the heat of formation of carbon atoms. So, of course, the molecule that you want to study, no one's going to know what it is, what the heat formation is. And so you're going to have to be able to estimate a lot of heats of formation. And the common way to do that is using the group additivity method. And that's based on the fact that experimentally, the heats of formation vary linearly with the number of carbon atoms for alkanes. So every time you add a CH2 group, you change the heat of formation by a set increment. And the same thing for the heat capacity. It changes pretty much by set increments. So each CH2 seems to have associated with it a certain amount of enthalpy and a certain amount of heat capacity. And it makes sense to some extent that if you add another CH2, it has another CH vibration, a CH bend vibration. They have a certain amount of heat capacity associated with them, how much they can hold. And so it works out that this should be about right. And this turns out to work out for a lot of different molecules. And so there's tables where people have worked this out for not just for alkanes, but lots and lots of different kinds of things. And a guy named Benson made a nice table of this back actually in the 70s. And then since then, people have started to add more and more functional group values to these tables. The tables are quite large, and so many, many molecules, you can treat them as like tinker toys. You glom a little bit of this, a little of this, like maybe Legos to you guys, Lego bricks. You stick them together, and then each one comes with it. This is worth 2 calories per mole Kelvin of heat capacity. This kind of Lego brick is worth 5 kcals per mole of enthalpy. Glom them together, now you just add them up. And it works not perfectly, but pretty well. And so that's usually the first estimate that people use because it doesn't take any time. And so if you go to this website in the web book, they have a group additivity program that has a lot of those there. The RMG, the Thurgas at Nancy, the Therm program, these guys all do the estimates. And so if you have any random molecule that no one's ever studied experimentally and no one's done a good calculation on, you can just go and just do this, and in 2 seconds you'll have an estimate of the enthalpy and the heat capacity and the entropy. And this is all related to the functional group idea of organic chemistry, that molecules really are like a sum of functional groups that are sort of not interacting that much, and you can treat them as just sort of separate, and each have their own properties, including things like the heat capacity and the enthalpy. All right, so problems though with this unfortunately, this works pretty good, and it's very great. I use it all the time, but it's not perfect. So one is that for ring molecules, so for example, for cyclopentane, if you just use the groups of CH2s and have 5 CH2 groups added together, see cyclopentane, draw it for you. So cyclopentane is a CH2, another CH2, another CH2. So if you just take 5 of these units and add them up, you add up their enthalpies, it doesn't work out. It doesn't give you the right heat of formation. It's you add them up, you get a negative 103 kilojoules per mole, but the experimental value is negative 76. So you're off almost 30 kilojoules per mole. And that's called the ring strain. And that's because the CH2 values were derived from straight chain alkanes that were like free to flop around. But now when I put them in the 5-member ring, it's kind of stiff and they're held there in an uncomfortable position. And so their energy is slightly different. And this is even worse if you have fused ring cyclics, like polycyclic aromatics. Then the group methods work more and more poorly. And then there's other cases, some halogenated compounds, some really branchy compounds also give very poor estimates by the group additivity method. And also if you have different resonance forms, so propargyl is a very important radical in combustion. So this is propargyl. But you can also draw it this way. So here would be a radical here, here would be a radical here. So this molecule is a little bit of each of these. The drawing is not good. But with the group methods would say, well, does this have like is this a CH2 radical group that I should use here? Or is this a CH2 group that's bonded to a double bond? those two things would have different enthalpies increments in the tables. So, so then it's not so clear for some molecules how to actually correctly use the group additivity. And the different way you draw the molecule, you might actually compute a different number. They won't be that different, but they'll be a little bit different. You don't know which one is the right one to use. All right, and then the final thing about thermochemistry is you can compute the equilibrium. So if you have all these numbers, like the enthalpies, the entropies, the heat capacities for all the molecules in your system, a really nice thing to do right away is just compute what's the equilibrium. So if everything ran as far as it could go in my conditions, what would I end up with? If I burn it all, what should it be? And there's a really nice programs that do this by minimizing the total free energy of the system. So you add up, you can write a formula for the whole free energy of the entire system as kind of a sum of free energies of all the little parts, including the entropy of mixing and the other terms that come from the concentrations. And when you do that, then you can just minimize the total free energy subject to the constraint that you have, so many atoms of each type in the box, and get the lowest, the true equilibrium state that the system could possibly achieve. And knowing that is often a really valuable thing to know right away. So I start with these reactants. This is where I will end up at infinite time. And then that, to me at least, it's often the first thing to do, because if you end up somewhere you don't want to go, then maybe you should stop right over this minute instead of trying to do something else. All right, so that's the end of the thermo. And now I'll start actually doing some kinetics. And before I start, I should say this is a very complicated field of great interest to many people. And so there are a lot of review articles. And your first page is just review articles. And I would say a good one to start with is the current status of trinity theory, this one up here, JPhys Chem volume 100. This is a really nice article. It kind of gives a study. Now it's 1996, so it's kind of old now. But if you haven't worked in this field, this is a really clear article. Some of these other ones are really good, but they're not as easy to read. So this is when you get more advanced. You look at those other ones. But I'd start with the first one there. All right. So to understand rate theory, we have to start with the Born-Oppenheimer approximation. And the Born-Oppenheimer approximation is saying that the electrons are very light, and they move around really fast. And the nuclei are really heavy and fat and slow by comparison. And so you could almost approximate that the nuclei are not moving from the point of view of the electrons. So it's just like when I'm out walking with my little kids. The little kids are like zooming around me like a cloud, and I'm slowly strolling along at my middle-aged pace, and the kids are like flying everywhere, okay? And the electrons are even faster than my kids, so they're really going everywhere. And so the approximation is to solve what the electrons would do if the nuclei were standing still, if they weren't moving at all, just frozen where they were, and figure out what the electrons would move. And then use the average position of the electrons to compute the forces on the nuclei at that position. And then move to a different nuclear position and do it again. And you can compute the energy at each point too. And you get that energy is called V of R, the potential energy. Now, computing the electron energy is really complicated because electrons are really wave-like. And you also have to satisfy the Pauli exclusion principle, which is also kind of complicated. And so the solvers that are used to compute V of R, compute from the electron's motion, those are really different than anything you guys would use for classical mechanics. Really nothing like it. And there's specialized techniques that have been developed for a long time to solve the electron motion problem. So typically, people in our community would just buy a quantum chemistry program like Gaussian or MolPro, or else we might get a free one like Games. But there's several of these programs are available. And then you would take one, and in that program, they've already worked nice numerical methods to solve the electron motion part. And basically, you just type in the positions of your atoms, of your nuclei, and it will compute what the energy is and what the forces are on the nuclei due to the electrons. So that's the way we usually start. So I'm going to assume we have that already. I'm not going to talk any more about how we do it. And instead, I'm going to worry about, suppose we had this V, and it depends on the positions of the nuclei, that I call capital R. How am I going to compute the rate coefficients K of T? Because that's what I want to know. All right, so let's back up and say, well, how would you do it in classical mechanics? Suppose somebody told you a V of R, a potential of some particles interacting with each other, and you wanted to compute it at a rate. What would that be? So the way that this is done is you would first assume ergodicity, which means that every possible configuration of the system of all these particles is like equally likely to happen. And in configuration, it's not just the positions, but it's also the momenta that matters, according to classical mechanics. And if you do that, then you say that's the ergodic assumption, and you just say that the only thing that matters is the energy. There's like a Boltzmann weighting factor, that the high energy configurations are less likely to be formed. And otherwise, anything is likely to happen. If you start by doing that, and now I need to figure out what do I call a reactant, what do I call a product. And I say, well, there's certain arrangements of the atoms where certain guys are close to each other, I call that the reactant. And then when that bond's broken, they're far apart from each other and they're doing something else, I call that the product. And so I have to be able to define for any positions Q of the atoms, is this in reactant part of the phase space or in this product part of the phase space? And I have to define a dividing boundary between the two. And once I have that boundary surface between the reactants and the products, then I can, for example, run trajectories and see, do the things cross that boundary? And the trajectories that cross that boundary are reactive trajectories, are going to make a reaction happen. And ones that never cross the boundary, those are just staying inside the reactant phase space or the product phase space. So I define a dividing surface S of Q, and I define the boundaries being when that's equal to 0. And so I can evaluate, if S is positive, I call it product. If S is negative, I call it reactant. If S is 0, it's on the boundary between reactant and product. And it's up to you as the user. You can define your own boundary. Because this is sort of the atoms are just wiggling around. They don't care if you call it methyl or you call it methane, right? They're just wiggling around any which way they want. And you, as the observer, is looking at them and saying, hey, oh, now it changed from methane to methyl. Because I saw this CH bond got beyond some distance, so far that I say that the bond's broken. Okay? And so there's the human has to decide what's that boundary. And the time that it takes to cross this boundary is related to the rate coefficient, and there's a statistical formula for that. So here's a picture. So over here, say, is my reactant or my product space. Suppose I'm starting over here. It's my reactant. I want to know, do I end up in this valley, which I call my product? And I divide my dividing surface right here, and I start a bunch of trajectories. And some of them go across the boundary and fall into the valley. And some of them might cross the boundary and then even turn around and go back. There's all kinds of things that can happen. And I want to know how many of them went across and actually end up over here. And so the rate coefficient is actually this integral of the probability of different starting positions. There's sort of a delta function at the boundary. And then there's a function that tells me whether it ends up in the product space or not. And another one that says what's the rate, the speed as it crosses the boundary. And if I put them all together in this integral, that turns out to be the formula that would give me the rate coefficient. And each of these are here. So this is the Boltzmann factor for a canonical system. If I assume that everything's in thermodynamic equilibrium, like in contact with a temperature bath. And here's the dividing surface. This is the velocity, is the momentum times divided by the mass. That's the velocity through the dividing surface. And this is the function that says it's 1 if the trajectory is reactive, which means in long time does it end up in this valley. And it's 0 if it doesn't, like this one. All right? And there's a textbook you could look up that has a whole chapter basically about this picture and what that form is. So that's the classical thing. If you watched a lot of manifestations of your system, started a lot of different trajectories at different points, and just counted how many end up as reactants and how long it took them, then you'd be able to calculate a rate coefficient, and this would actually be the integral that you would do to calculate it. Now, if I make some assumptions, if I assume that this chi factor here is close to 1, that means almost everything that crosses the boundary goes to the valley. If I assume that's true, then I can simplify my math. So if I assume it's called no recrossing, and if I make a special choice of how I define my dividing surface, then I can actually analytically solve those integrals. And they turn out to be this. Or I can write it in this cute way, where this thing here is this integral, a Boltzmann factor, evaluated when at the dividing surface, basically. And this other one is the regular partition function we had before, the classical version of that. The theta function is the Heaviside functions. It's 1 if q is greater than 0, and 0 otherwise. And this is the energy of the mountain pass, or the lowest energy at the dividing surface. So it's the minimum energy required to get across. So this formula is the formula for the rate coefficient if I believe that the recrossings are negligible, and I believe classical mechanics, everything's fine. So this was known a long time ago, actually, as the statistical mechanics formula for things. And they use it for the rings of Saturn. There's particles in the rings of Saturn flying around, and they want to know how likely it is that they'll move from one ring position to another ring position. So they can calculate a rate. There's a dividing surface between the two rings, calculate the trajectories, what's the chance that they would go through if they were randomly moving around, stuff like that. So those kind of problems they do. When they try to figure out the origins of galactic nuclei, stuff like that, they'll run a million little bits of ice and rocks out in space and see what's the probability that they would end up all glommed together to make a black hole or something. Okay? So that's the kind of stuff that the classical mechanics guys have been doing for a long time. And let's get this for a minute. Well, let's just look at this for a minute. So the main assumption we made was that we assumed all the trajectories with positive velocity through the dividing surface are reactive, are going to go to products. So that replaced this chi with a Heaviside function. Because we did this, our rate coefficient is always an overestimate, because chi is normally, it can be like 0 or 1, it's reactive or not reactive. We assume they're all reactive. So we chose it to be the maximum value. So we always are going to overestimate what the real rate is. So the k that's calculated by transition state theory with that assumption is always greater than or equal to the real rate you would get. And so this implies there's a variational principle. And so that leads to an idea of variational transition state theory, where you say, well, let's try different dividing surfaces, and we'll try to find the dividing surface that gives the smallest rate, and that should be the closest to the truth. And so the idea is we're trying to find, here, we draw this dividing surface, but this is kind of like, how do we know it's really exactly here? Maybe it could be right here instead. And maybe it was here, then this trajectory B would all be in the reactant space and never even cross the boundary at all. And so therefore, we wouldn't make the overestimate of counting this guy crossing as a reaction. Does that make sense? So you have a choice of where to define the S, and the correct choice of S would be the one that gives you the smallest number for the rate. And so then you can try to run a rate calculation for one assumed value of S, then try a different value of S, a different dividing surface, try again, keep trying over and over again. The dividing surface you find that has the smallest rate is the one closest to the truth. And that's called variational transition state theory.
Is this still overestimated?
That one actually is in classical mechanics. It's still an overestimate because you never can find the perfect dividing surface. But you're getting closer and closer. You're like from above. You're always overestimating, and you're getting closer and closer to the truth as you get better and better dividing surfaces. And usually you draw more and more complicated ones to try to make it minimized. But typically people get tired of doing it before they've done too many. So they might try 100 different dividing surfaces and pick the one that's the smallest rate and say, okay, good enough, I'm done. Yeah. All right, so this is an approximate theory, obviously. So why do people use this? So let's go back to the beginning. When we build a model for our fuel, we're going to need 1,000 rate coefficients or more. And when you look up in the NIST web book, you'll find that there's 100 have been measured. So I need 900 additional rate coefficients from somewhere. And so I can't afford to do 900 experiments to measure 900 rate coefficients. That's not inside my grant budget. So instead, I better calculate them. And in fact, I often can't even perform the experiments at all at the temperature and pressure I care about for combustion, because often I care about 1,500 Kelvin and 100 atmospheres in some diesel engine, and I don't know how to do any experiments in that condition. So I can't tell any rate coefficients experimentally. So I'll do theory. Now, what can I do theoretically? I could do empirical models where I try to extrapolate basically from related experiments. Sometimes this works, but this is like highly fraught with problems because it's like based on you knowing how similar your new reaction is to some old reaction, that's some different reaction. And they could be similar, but it might not be. So this is a problem. So greater accuracy is definitely desirable. You could run classical trajectories just like they did in the old days of the 19th century, or just like the guys do, the rings of Saturn guys do. And you can do it. And the problem with this is you need to have a potential energy surface evaluated at all positions. This is a problem. And there'll be no quantum effects in this. But even the killer problem for this is that the time scale, when you try to do this, it turns out for atoms, they move so fast that in order to integrate them, you have to use a delta t time step in femtoseconds. And so you need a heck of a lot of time steps, even to get up to 1 nanosecond of real time of the motion of the atoms. But a lot of reactions happen on time scales of like 100 milliseconds, something like that. And that's like many orders of magnitude longer than a nanosecond. So if you do just run trajectories of how the atoms are wiggling around, there's many reactions you'll never see. It's very unlikely you'll see them because they're rare events. And the only reason we see them in our real systems is we have 10 to the 23rd molecules. But you can't afford to run 10 to the 23rd trajectories in your system, so you don't sample all the rare events. And so actually this is a very poor way to do the kinetics. You could try to do exact quantum mechanics and solve the Schrodinger equation. This is just ridiculous. You can only afford to do 4-atom systems with that. Actually, one guy did a 5-atom system once. Okay, so that's right out. So we can't do exact quantum mechanics. We can't even do classical mechanics because it's too expensive to run it long enough to see anything. The empirical methods are not reliable, so we're kind of forced to some approximate quantum theory is what we have to do. And the transition state theory turns out to be the best one that people have found so far. We can't completely ignore the quantum mechanics. So as we said before, we're computing the partition functions. We have to, for the vibrations, we had a 0-point energy. Do you guys remember this? So the 0-point energy, the fact that we have quantized energy levels, means obviously quantum mechanics is important because otherwise we would have continuous energy levels. And all our partition functions and our thermo would be a lot different. So it's important for vibrations at least are quantized. And so then you say, well, what I told you so far is all classical trajectories. That's how I derive my transition state theory. So how can I put the quantum in? Now, there is an exact quantum mechanical operator that actually works and corresponds to the classical phase-space integrals that show up in this rate theory. And a guy named Bill Miller at Berkeley, he's written a lot of papers about this, showing the exact, there's an exact quantum mechanical analog to everything I showed you today, every classical thing. The exact version of this is super expensive, and so the biggest one they did was a 5-atom case so far. There's a bunch of different approximate ways to go forward, but I would say that none of them have really been demonstrated to be that great. Or else the ones that have been pretty good have been super expensive. So it's really not really solved. Now, some people just say, forget it. Quantum mechanics is too much of a pain. Let's just do classical mechanics anyway. But this turns out that the 0-point energy effect is actually really pretty huge for kinetics. So it's not such a big deal for thermo, but it turns out for kinetics it's really enormous. So this is a big problem. And then there's the rare event sampling problem is very often a big problem for kinetics. And then some people have tried to patch up molecular dynamics to try to fix the 0-point problem. And so, for example, I was working on a method called RPMD, and there's a couple other methods that do this. And that's a possibility, but they don't really overcome the nanosecond problem. So you can't really run reactions, rare events you might not sample, because you're just sampling trajectories. You need a lot of your trajectories to do the reaction you're trying to study to get good statistics. And so this is a problem. So again, we have a problem. So we need to have some way that we can do it that's cheap and convenient and actually pretty accurate. And it turns out the transition state is the way to do it. And there's a method called conventional transition state theory. And this is the way everybody does it, basically. And here's the recipe. First of all, you get those Q's I had in my equation from classical mechanics, and I replace them with my normal rigid rotor harmonic oscillator formulas that I already showed you for the thermochemistry. Just use the same formulas as I did for thermochemistry. Everywhere I see a Q trans, I use Q trans divided by V over N instead of the traditional Q trans that was proportional to V. So I get rid of the V in my Q trans. Otherwise, I'm just using stat mech. Everywhere I see an E, I correct it with 0-point energy difference between the reactants and the transition state. And if my transition state has a mirror image, I just multiply the rate by a factor of 2, so I can go left-hand way or right-hand way. And then I'm going to finally correct it by a little tiny tunneling correction. I'll tell you about that later. It's not usually a big deal. And so what's the procedure? First, I have to find the geometry that minimizes the energy for the reactants and also for the transition state. Usually that's a saddle point. And typically this is done with some DFT calculation. And this is the first hard thing you have to do. So you buy a program like Gaussian, you guess what you think the saddle point geometry is like. Gaussian tells you that's not a saddle point. You say, okay, keep looking. And Gaussian tries to chug around, moves the atoms around, try to find some geometry that corresponds to a saddle point in the potential surface. Then you do the same thing for the minimum of the reactants. And then the difference between those two energies is very important. That's going to be the barrier height, the E. And so I'll try to do that with the highest level quantum calculation I can afford to do. I also try to calculate the second derivatives as accurately as I can afford to do. And now I have these second derivatives will give me the frequencies that I need to compute the Qs. This energy at the saddle point, the energy difference, that's the E. So if you look back at the formula, where was the formula? Here. I need Qs and I need an E. So the Qs are from vibrational frequencies. The E is from the energy difference between the reactants and the barrier height. So I get them. I just plug, once I get those numbers, the E's and the frequencies, I plug them into the StatMech formulas for the Qs, and bing, I have a number, KFT. Okay? And if I'm lucky, this number is really close to the truth. All right? But now you get the idea this is like not guaranteed that this will really be the truth, but sometimes, a lot of times it is. So people use this a lot because it works pretty well. There's some minor things. You can have multiple different ways that you can react. So for example, I have an OH abstraction from methane. There's 4 different hydrogens on methane. So I really have like 4 times as many reactions as you might think because I can abstract each different H. So somehow there should be a factor of 4 in the rate. So this is the recipe about how to make sure you have the right factors of 4 and factors of 2 and stuff you have. It's all about the symmetry numbers and the mirror images. Here's a nice little check you guys should maybe do as homework. If you have a forward rate that has this formula, that's the transition theory formula, and a reverse rate that has this formula, where the difference is now that instead of having the reactants, you're now coming from the products. And so you have the products here instead of the reactants in the energy difference. If I compute the Kc, that's the ratio of these two guys, what is it? Well, all the transition state properties cancel out, and I end up with a ratio of the Qs of the products to the reactants and the energy difference of the products to the reactants. And this is exactly what you calculate from the StatMech, from the delta G of the reaction. So this looks good. So at least we're consistent. Even if we're not exactly accurate, at least we're consistent. All right, so homework. I want you to compute the reaction of C6H7 spitting out H atom to become benzene plus H. So calculate this rate. These guys determined the delta H for this reaction very accurately, 322 kilojoules per mole. Tsang gave an estimate of the entropy of formation of C6H7, this number here. And let's say to a first approximation, let's assume that the Qs for the transition state and for the reactant are about the same because the transition state looks like the reactant with just the CH bond stretched a little bit. So it shouldn't be that much different. So if you make that approximation, if you use their numbers, can you compute what KFT is? And what are the units of KFT? That's also a good question for you. And then does this follow the Arrhenius rate law or not? That would be a good question. Maybe you can make a little sketch of what KFT looks like. And then you can use the thermo, try to calculate the reverse rate coefficient for H atom to benzene, and check the units also, because the units are different. All right, so here's your homework problem. We can talk about this tomorrow. See if you can figure out how to do it. And again, this is not a graded class. However, if you try to do this, I think it will wake up your mind to many of the issues you have to deal with when you're trying to do rate calculations. All right. Let's take a kind of quickly wrap up here. So what I showed you before, everything so far, I started from classical mechanics where I assumed I had a temperature, T. So I assumed everything was in contact with a thermal bath, and the temperature was held, maintained, the energy followed perfect Boltzmann distribution. It was perfect temperature. In some of the systems we have, there is no good thermal bath. So we're way out of equilibrium, out of thermal equilibrium. And so you can have some species that are super hot, super energized, compared to what the rest of the molecules are. It can happen. And what can happen is that the reactions can get so fast that you don't have enough collisions to bring the things back into thermal equilibrium, to reestablish the temperature. So you run an exothermic reaction, you run it super fast, the products are formed really hot, much hotter than the bath temperature. And the bath gas is colliding with them and gradually cooling them down, but that rate of cooling can be slow compared to the rate of the reaction, and so you'll get out of equilibrium. In that case, you really don't want K of T, you want K of E. You want to know the microcanonical rate, how it depends with the energy of the reactants. And you can do the exact same derivation that I did above for K of E instead of K of T. And in fact, up on the first slide about the theory, here I said if you're doing microcanonical, you should just use a different value for P. So you just say it's a delta function. The energy is whatever value it is, instead of using a Boltzmann factor, which is what that is. The beta here is 1 over KT. Yeah. Okay. So if you just plug this in, now you have the same formula, just a different expression for the probability of the trajectories. Only take the trajectories that have the right energy to correspond to E. All right. So if you do that and just analytically solve the integrals, you end up with this, where N of E is a sum of Heaviside functions of all the energies of the system. So instead of having the partition function Q, instead you get just a sum of the states that have energies that are below the total energy are allowed, they contribute, and all the ones that have higher energies are not involved. They're 0. And also then this quantity in the denominator is just a derivative of this guy. Now, I believe that Wigner knew this formula, but unfortunately, he didn't write it down that clearly. And at the same time he wrote his paper, another guy named Eyring wrote a paper where he wrote a different derivation of the canonical transition state theory. And Eyring was a chemist, and Wigner was a physicist. And the physicists all read Wigner's paper, and the chemists all read Eyring's paper. And Eyring didn't know this. So the chemists had no idea what K of E was at this point. And so these guys, Rice, Ramsperger, and Castle, realized that K of E is very important in combustion, and they tried to figure out what it was. And they made up a theory that's sort of semi-reasonable called RK theory, named after their first initials. And people use this for a while, but it's not really right. And then a guy named Rudy Marcus came along, and he read the RK paper, and he said, it's not quite right, but I figured out how to correct it, and I end up with this formula. And he wrote that down. It's called the Arkam Formula, because he added his name, M, at the end of the RK. And that formula is now what chemists would normally, they would call this equation the Arkam equation. For reasons I don't understand, there was a huge controversy about this. I don't know why. And people didn't believe Marcus when he said that this was the right thing. And people kept making up new formulas for K of E. And this went on for like 20 years. And there were like 15 different proposed K of E formulas about how the rate should depend on the energy. And part of what was going on is if you look at this formula carefully, it's kind of strange. Because this N of E is a sum of Heaviside functions, so it has discontinuities. It jumps. And I think the chemists were just really not happy to have a discontinuous rate. It just didn't seem right. So the other theories that proposed things, they had nice smooth rates that just smoothly rose up with E. And nobody ever observed these kind of jumps anyway. So anyway, it was a big controversy. And then in the 1980s, the rate was measured as a function of energy, and look what you got. Jumps. And so this looks like a sum of heaviside functions on the way up here, right? Chunk, chunk, chunk. And so then after this, everybody realized, oh yeah, Marcus was right in the first place. And actually, then people went back and looked at the Wigner paper, which actually showed the same thing. And so this is the truth, that the rates are actually quantized. However, the quantization is very fine. So only if you do a very careful experiment. So this was done 4 Kelvin. So only at very low temperatures can you see it experimentally, the quantization. Usually everything looks smooth because it's so Boltzmann averaged out. It's also all averaged out. But this sort of proves that the formula is actually correct in principle. And actually after this, then Miller did the theoretical calculations, the theoretical work to show that the real Schrodinger equation gives this exact K of E formula. And the real quantum mechanical operator for what N of E should be, which has kinks in it, just like this. So everybody believes it now. If you do a Boltzmann average of the K of E, you get exactly the same K of T that we did before. Here's the derivation. But this whole thing leads to another detailed balance. So before I told you the detailed balance, which I think is right here. If you have a reaction, its net rate is this minus that, forward minus reverse. So at equilibrium, the forward must equal the reverse. And that's how you get the relationship that the forward over reverse is equal to Kc. Okay? You can do the same thing microcanonically. And when you do it microcanonically, you get the expression up at the top there, that the density of states of the reactants times the forward rate coefficient, a function of energy, has got to be equal to density state of the products times the reverse. And both of these guys are equal to N of E over H from the rate law, from the expression up here. So you can just see that, right? Times rho times K is equal to N over H. It doesn't matter if it's products or reactants, it'll be the same. So this gives you an additional constraint about what the K of E's have to be. So if you have a forward K of E, you immediately know the reverse K of E. Of course, you have to calculate the density of states, which is slightly complicated, but you can do it. And there's all about how you calculate density of states. There's a guy named Beyer-Swinehart figured out how to do this. This is also in textbooks. And I think I'll stop right here. Let's just take another break.